Hello students, welcome to the class of Digital Signal Processing, and today we are going to discuss discrete Fourier transform, which is explicitly mentioned in your syllabus module 3. And we were doing DTFS, DTFT, always, all those were part of the discrete time Fourier analysis. So basically the thing that was written in your syllabus was Fourier analysis. So we did all those things very quickly, like I tried to introduce every part of the Fourier analysis, but the main part which is given in your syllabus, which is mentioned is DFT. But since Fourier analysis was mentioned, I also covered those portions. Now let us today get started with DFT. First thing was first I'll start with the very basic thing, that is the three parts of it, which we have already done. So how the questions can come and what else things you have to notice. So the first thing that is given in your syllabus is Fourier analysis. So there can be a short definition which you might be asked, like what is Fourier analysis? But in this definition, or this may or may not be asked. But after this, we also did DTFS and DTFT. And today what we are going to do is DFT. So first of all, the major thing that you have to understand that in Fourier analysis, in your syllabus, only we are doing the discrete portion. As if nothing is mentioned about the continuous portion. Also, the name of the subject is digital signal processing. So here all we are dealing is with discrete signals. Now first, I started with DTFS, where my signal Xn is discrete and periodic. Discrete and periodic. And you took in the time domain, this is discrete and periodic. So in the time domain, it was discrete and periodic. And when you took the Fourier transform in the frequency domain, also this signal remained discrete and periodic. But the portion was that the important thing was that you can only include periodic signals in this one, and you are taking out a harmonic analysis you are doing for finding the discrete time Fourier series. When you are taking series, that means you will have periodic signal, and you are doing harmonic analysis, means what are the frequency components present, and in terms of the harmonics of that fundamental frequency. So we introduced DTFT, where we can deal with aperiodic signals. So here my Xn was discrete but aperiodic, or you can say non-periodic. So we included the aperiodic signal in this. We also talked about that we can include periodic signal for this, means DTFT can be applicable for both of the cases, but this one cannot be applied for aperiodic. So what we did was we took this discrete and aperiodic part for DTFT, and what we got in the frequency spectrum was continuous and periodic. Now what's the problem that is arising is the continuous signal. In the frequency domain, the signal is continuous, so it cannot be processed with digital systems like computers, laptops, etc. So what we are doing in case of DFT, that is the discrete Fourier transform, we are sampling the DTFT. Sampling DTFT means sampling the DTFT, or the frequency part of the signal. Or we say that we are taking Xn, which is discrete. It can be periodic or aperiodic, that is the second part, but it should be finite. Finite is the more important word here. In this case, the length of the signal could be infinite, but here it has to be finite. Periodic is there. Periodic and aperiodic, both it can be, but the important thing over here is it has to be finite. And in terms of frequency domain, if you see, then this part, continuous portion, we are going to make it discrete. So all the things which are necessary for a digital processing, that is both in the frequency and the time domain, in the time domain also, and in the frequency domain also, my signal became discrete, periodic, finite. So this is the reason of introducing discrete Fourier transform, which is basically the sampled version of DTFT. Okay. Now, to analyze this, first we have to know the how we denote it. So xn, if you do the DFT of this, you will be denoting it by x of k. And if xk you take and you do the IDFT of this, what you get is x of n. Now, very important thing that you have to understand is these are all complex. So we are going to have the real part also and imaginary part also. So for whenever you are taking the magnitude part for a complex signal, how do you get it? Real part whole square plus imaginary part whole square. This is the same way you will get the magnitude spectrum. So in the frequency spectrum, you have magnitude spectra and phase spectra. So for getting the magnitude spectra, you will take the real part plus whole square plus imaginary part whole square under the root. For the phase spectra, what you need to do is tan inverse, right? Tan inverse of the imaginary part by the real part. This is one of it. Now let me write the actual xk. That is the DFT of the signal. Fine. So x of k is given as n equals to 0 to n minus 1, x of n e to the power of minus j 2 pi k n by capital N, where k is equal to 0, 1, 2, up to n minus 1, and also small n is equal to 0, 1, 2, up to n minus 1. So this thing you saw in case of discrete time Fourier series also, that there were two things, that is k and n. N is your time instance and k is the exponential, different exponential. I explained this part there. Different exponentials, you can take it. So this important thing is that xk is periodic in both n and k. In both k and n. So, sorry, this is small n. Both small k and small n. So, if you write xk plus capital N, that will be equal to xk. If you write x small n plus n, that will be equal to x of n. Now, what is the meaning of this? K means different exponentials and n means different time instants. If I try to show you with the help of graph, I've already shown this. So this is an exponential. This is also exponential. This is also exponential. So all these exponentials are going to have, see, this is e to the power x. This can be e to the power 3x or 2x, whatever you take it. 1 plus something will be there, but I'll just write it. And this will be something different. So this is my different case. This denote different case. And how we take different n? These are my different n. The time instance. And for a single k, you have different n. right? For this k, you have different n's. So this is a method of understanding the meaning of k and n, which also I have discussed in case when we were doing discrete time Fourier series. Now, what is the important difference between here and there is that your here signal can be periodic and aperiodic, and after sampling the DTFT, you are making it finite and periodic. So this is the one thing that you have to keep in mind. And you have to make the signal finite, means sampling of the DTFT, sampling of DTFT will is giving me DFT. This sampling has to obey the Nyquist criteria so that there is no aliasing. And that is the way we decide our capital N. Okay. Now, if you take the inverse of this, that is the IDFT, inverse discrete Fourier transform. That time it is given as x of n is equal to 1 by n, k is equals to 0 to capital N minus 1, xk e to the power of j 2 pi k n by n. Again, here also small n is going from 0 to n minus 1 and small k is going to from 0 to capital N minus 1. So this thing is happening in both the cases. The k and n is varying from 0 to n minus 1. So again, the properties of the DFT, it is going to be the same, the linearity property. So first what I'll do is we'll do some questions first. After that, we will be doing the property. One question on DFT and one question on how to find the IDFT. And then we will go on with the properties. Fine. So let's get started. And one more important thing over here that you keep in mind, that this point, when you are writing e to the power minus j 2 pi k n by n, right? Or e to the power j 2 pi k n by n. There is just a difference of minus and plus. In case of DFT, you use this minus. In case of IDFT, you use the plus. Same thing you have to remember for inverse DTFT also. This is plus, this is minus, but these things are not there. K and n is not there, just n is there. Okay, now here what you have to understand is e to the power minus j 2 pi by n. This has been given a special name, which is called the twiddle factor. Now, this twiddle factor has two properties. One is the symmetry property, and the other one is the periodicity property. But these two properties are not utilized in finding the DFT. For finding the DFT, we don't utilize the symmetry and periodicity property of the twiddle factor. So, there were several algorithms developed which are given the name of fast Fourier transform. Fast Fourier transform. It makes the Fourier transform or the DFT faster by utilizing these two properties, that is the symmetry and the periodicity property. Okay, this was a small description of DFT. Now let's calculate this DFT. Okay, so suppose we have been given a sequence. Question is find 4-point DFT, 4-point DFT of x of n given as 1, -2, 3, and 4. So this is at 0. Okay. So you know the formula right now. X of k is equal to small n is equals to 0 to capital N minus 1 xn e to the power minus j 2 pi k n by, right? N is ranging from 0 to n minus 1, and same thing with k. K is ranging from 0 to n minus 1. Now, what is capital N? This is called the length of the sequence. So in this case, the length of the sequence is 4, right? 1, 2, 3, 4 numbers are present here. So the length of the sequence is 4. And small n is going from 0 to 3. And small k will also be starting from 0, 1, 2, and 3. Now let us go ahead and find it. Okay. Now one thing you see. Okay, first let us find it. So how to find it is, first you will find x of 0. Now you know that this is also discrete and finite, and this is also discrete and finite, and also it is periodic. So what we are going to do is, first we will find for x of 0. See it very carefully. Okay. Now, if I write it x of 0, you know the formula. Now here I am writing, it has to be small x of 0, e to the power minus j 2 pi k into what? The k is 0 here. This is standing for k. K is 0. N is also 0 by capital N, 4, plus x1. So see, k will be 0 for all of them. Now here, e to the power minus j2 pi 0 into 1 by n. But since k is 0, so what is going to happen? E to the power that thing is going to become 1. So here it is simply x0 plus x1 plus x2 plus x3. Because k is 0. So what you will get is simply x0, which was 1, x1, which was minus 2, x2, which was 3, and plus 4. So this will give you 7 plus 1, 8, minus 2, 6. So x0 at k equals to 0, x0 is 6. Now if you find at k equals to 1, so see what I'll do is, first I will find out separately e to the power minus j2 pi k n by n. So you know that k is remaining fixed. Only thing is changing is small n. So what I have to do is e to the power minus j2 pi into 1 by 4 into n. How much will this be? E to the power minus j pi 2 into n. Got it? Now this is going to be cos pi n by 2 minus j sin pi n by 2. So the value of small n will range from 0 to 3. You know that. So when you're taking 0, that time this is going to become 0. Okay, we will not go till here. Just take it till here. After that, we will use this part next. Okay, now let us take out this x1. So x1 is small x0. Again, I'm writing it, then you'll understand. So capital X0 we have calculated by the formula xk equals to n is equals to 0 to capital N minus 1 x of n e to the power minus j2 pi k n by capital N. So now we are going to have x0 e to the power. How much was that? We'll not take everywhere, that, right? So here we have 0 to 3 power. So 0 to 3 power, 1 by 2 into 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 1 by 2 just we will take e to the power minus j pi by 2 into n, because we have already utilized the value of k. K is everywhere 1 for this case, because we are taking out for x 1 right now, right? So it is going to be e to the power minus j pi by 2 into 0. Then x1 e to the power minus j pi by 2 into 1 plus x2 e to the power minus j pi by 2 into 2 plus x3 e to the power minus j pi by 2 into 3. Got it? Now x0, this portion is going to become 1. This is equal to 1. So x0, the value was 1. x1, the value was minus 2. Now here you have cos pi by 2 minus j sin pi by 2. Fine. Now x2 is what? 3. Now this is 2 and 2 getting cancelled. So you'll get cos pi minus j sin pi plus x3 is how much? It is 4. And this is cos 3 pi by 2 minus j sin 3 pi by 2 minus j sin 3 pi by. So now this is x of 1, right? This is all we are writing for x of 1. X of 1. This is equal to 1 minus cos pi by 2 is 0. So you have plus 2j. Here cos pi is minus 1 and this is 0. So it is minus 3. In this case, this is going to be 0 and this is minus 1. So plus 4j. So finally what you get is minus 2 plus 6j. That is the value of x of 1. We have already got x of 0. Now we'll calculate x of 2. Capital X2. So this value of 2 is for what? Is it for k or for n? It is for k. So first step, find out e to the power minus j2 pi k n by n by putting the value of k and n. So that will simplify the process there. By 4 into n. So it is simplified to e to the power minus j pi n. Now we'll start writing it. So here it is x of 2, x0 e to the power minus j pi into 0. It was minus j pi n, right? Plus x1 e to the power minus j pi 1 plus x2 e to the power minus j pi 2 plus x3 e to the power minus j pi 3. So the value of x of 0 was 1. This whole thing is going to become 1. So 1. x1, the value was minus 2. And this is going to be cos pi minus j sin pi. Plus the value was 3 here for x2. Cos 2 pi minus j sin 2 pi. Now the value was 4 cos 3 pi minus j sin 3 pi. Now we will calculate this value. So this is okay, 1. Cos pi, the value is minus 1, so it is 2. Cos 2 pi, the value will be 1. Again, cos 3 pi, the value will be minus 1. So what you get is 2. With sin pi, sin 2 pi, sin 3 pi, all will be 0. Final one is taking out x of 3. Because it is capital N is 4, so you will go from 0 to 3. Now again for this, first we will take out e to the power minus j2 pi kn by n. So this is equal to e to the power minus j2 pi into 3 into n by 4. Now this is going to get cancelled by 2. So this boils down to e to the power minus j3 pi by 2 into n. Fine. Now take out the values. So the first one is x of 0. By now you know e to the power anything 0 will be 1. So x1 e to the power minus j3 pi n by 2 plus x2 e to the power minus j3 pi n by 2 plus x3 e to the power minus j3 pi n by 2. Now, the value of x0 was given as 1. x2, the value was minus 2, and this is cos 3 pi n by 2. So n over here is 1, so 3 pi by 2 minus j sine 3 pi by 2. The x2 value was 3. Again here n is 2, so cos 3 pi minus j sine 3 pi. The last one, that is x3, was 4. And here it is cos. So here it was 3, right? So this is going to become cos 9 pi by 2 minus j sine 9 pi by. Now if you write it, this is going to become 1 minus, this will be 0. This is going to be minus 1. So minus 2j plus this one, if you see over here, this is going to be 0 and this is going to be minus 1. So it is going to be minus 3. Now this one, cos 9 pi by 2 will be 0. And this one, if you see, it is sine pi by 2 is 1. 3 pi by 2 is minus 1. 5 pi by 2 is 1. 7 pi by 2 is minus 1. After that, 9 pi by 2 is positive 1. So the value is 4 minus j. So finally, it is minus 2 minus 6j. So what you get final answer is your xk, which is the value for x0. Just see it. You'll have to scroll up and see. See, the value for x1 is minus 2 plus j6. Keep it in mind. For x0, it is 6. x0, it is 6. x1 is minus 2 plus 6j. x2 is 2. And x3 is minus 2 minus 6j. So x0 was 6. x1 was minus 2 plus 6j. Again, it was 2. And the last one is minus 2 minus 6j. So this is the way to find out the DFT. This was just a 4-point DFT and it took a long time to calculate it. So calculation has to be, the property of Twiddle factor needs to be utilized. So in this class, we are doing we have taken out the DFT. In the next class, we'll do one question on IDFT and we will understand how the Twiddle factor works. And then we will start with the properties. Or what we can do is the Twiddle factor part, since it is useful in the fast Fourier transform, I will tell the importance of Twiddle factor there only. Next class, we'll do one question on IDFT and we'll start with the properties. Thank you, everyone.